This is an empirical formula by combustion analysis problem. You are told from the problem statement that you have 2.78 milligrams of ethyl butyrate. We want to know its empirical formula. You're also told that after combustion you have 6.32 milligrams of carbon dioxide and 2.58 milligrams of water. That's given in the problem statement. We know that ethyl butyrate contains carbon, hydrogen, and oxygen. So our beginning analysis is to think what happens when you combust ethyl butyrate. Even if you don't know what its formula is, you do know that in any combustion you are going to have a hydrocarbon and oxygen that will react to form carbon dioxide and water. You also know that the subscripts for carbon will also be the coefficient of carbon dioxide on the product side. I will not be able to get any carbons for carbon dioxide from anywhere other than the carbon that was in the original hydrocarbon. I will not be able to get hydrogens for water from anywhere other than the hydrogen that was in the original compound. There is a little odd thing there that if I had, say, 5 hydrogens in the original carbon or in the original hydrocarbon, I would not produce 5 molecules of water. I would produce 2.5 molecules of water because of the subscripts. It takes 2 hydrogens to make 1 water molecule. So this information will allow us to work backwards, essentially. You're going to begin at the end. Begin by knowing about the carbon dioxide and the water to figure out how much carbon and hydrogen I had to have started with. So we start with the carbon dioxide amount that we knew, convert to grams, and use molar mass of carbon dioxide to find moles of carbon dioxide. Then use stoichiometry to know that if I had a mole of carbon dioxide, that had to have come from 1 mole or would require 1 mole of carbon. Molar mass of carbon gives you the grams of carbon in your original sample. Very similar process for water, converting to grams to moles of water. Again, this is why you always need to write the unit and the substance. Moles of water. 1 mole of water required 2 moles of hydrogen atoms, and again convert to grams. This gives us the grams of carbon and the grams of hydrogen that you were starting with. Oxygen is a little different. Oxygen has to be everything else. That I have a certain known amount of the sample to begin with. If I subtract off how much of that original sample was carbon and how much of that original sample was hydrogen, the rest of it must be oxygen by elimination. Should be relatively reasonable numbers. They should be on similar orders of magnitude if everything is going well. What we're doing here is the first step of the little mnemonic that you use for empirical formula. Usually it starts with percent to mass to moles, divide by least, multiply to whole. We don't need percent to mass because we didn't start with percents. Instead, we start with mass essentially, and we need to get to moles. So the first slide gave you the mass of carbon, the mass of hydrogen, the mass of oxygen, so that you could now do the rest of the mnemonic. I know I take grams of carbon to moles of carbon, grams of hydrogen to moles of hydrogen. And you might wonder why you didn't just stop at moles before. The reason is because you had to go all the way to mass so that you could figure out the mass of oxygen. If you had stopped at moles on the previous slide, you wouldn't have any idea how much oxygen you had. So now you have that oxygen number and you can go ahead and get to moles of oxygen. The rest of this is very similar to what you have done in other empirical formula problems. So now you know moles, so now you can do ratio. Find what the smallest number is, being careful about those exponents. You're looking for the biggest negative exponent. And then divide by whatever that smallest number, which is, of course, then a big negative exponent. You should get reasonable numbers for this. I'm not sure I've ever seen one. I'm not saying it doesn't exist, but I'm not sure I've ever seen one that you did have to multiply to a whole. Usually they come out correct, like this. So 2.97 is very close to 3, 5.95 is very close to 6, and oxygen is 1 for sure. So your empirical formula is C3H6O. Remember that the empirical formula does not tell you the number of atoms in a molecule, it just gives you the lowest ratio. In order to know the molecular formula, how many atoms would be in a molecule of ethyl butyrate, you would have to have additional information about molar mass. But you have successfully found the empirical formula.